Okay, in this video we're going to go over lesson 7, exponential modeling. So this is a topic that we have looked at last unit when we were studying exponential functions. However, we were never able to look at a modeling question last unit and solve for time unless we were able to use the one method of solving exponential functions that we had, which was common bases. Typically, a modeling question will not work out that way. And now that we have the ability of using logarithms to solve exponential equations, we are able to solve for time in modeling questions dealing with exponential functions. So let's take a moment to look at question 1. What I'd like you to do is actually pause the video, read through the first part of the question. There are 2 questions here, and see if you can answer the first part, and then we'll go over it. Okay, so they give you a function here, and they tell you that since January 1980, the population of this city has grown according to this mathematical model. We have X being the number of years since January 1980. Explain what the numbers mean and represent in this model. So the 720,500 and the 1.022. So if you were thinking that the 720,500 was the initial population, that is correct. So the initial population of, the city of Brownville. You could even say initial population of Brownville in January 1980 if you want to, since they did give you context to know exactly when. But if you also just wrote the initial population of the city of Brownville, that would be correct as well. Okay, now the 1.022, what this number is allowing us to see is the growth rate, which is 2.2% annual growth. Since X is the number of years, we know the rate would be based on that same time reference. So the rate is years since the exponent is years. And again, let me just rewrite that function so we can look at it here. So this time reference here should always match up with this time reference. We know that this is number of years, so this is also years. Okay, so that's the first part of this question, just breaking down what these 2 values tell us. Now what we're being asked to do is use this model to predict the year that the population will reach 1,548,800. So that's the amount for Y. And we're solving for time. So we need to somehow solve for that variable in our exponent. So I want you to take a minute. We have a few options using logs, or I should say really 2 options based on what we did yesterday in lesson 6. I want you to pause the video and give either of them a try. One is converting to log form, and one is taking the log of both sides to use the power rule of logs. Okay, so no matter which method you start with, first step has to be isolate the base. So we're going to divide by 720,500. Okay, so let's go to our calculator. Okay, so we have 1,548,800 divided by 720,500. You could write, the approximate decimal, or I know sometimes people will turn it into like the simplified fraction. I'm just going to write 2.149 and not round this. I'm just going to put a ... So I'm going to continue to use that full decimal, leave it in my calculator, you don't really need the parentheses here anymore anyway. Okay, so we isolated the base of 1.022. Now, if we're going to convert, I'll show you both ways. So we're going to convert to log form. That means we're going to circle the base, run the race, which means this is going to look like a log with a base of 1.022 of that 2.149 number, and it's equal to x. So really this just becomes one big plug-in. So alpha window choice 5 gets us the log base. The base is the 1.022 value. And now inside the logarithm, I want to put that decimal. So on the 84, you can just scroll up and hit enter, but I've had trouble with this calculator kind of doing what I want it to do with copy and pasting sometimes. So I'm just going to type in the simplified fraction. Either way, that 2.1496 full decimal value needs to go in the log, or, you know, even the original fraction, the 1,548,800 divided by the 725. However you want to do that, that number needs to go in the parenthesis. I just put in the simplified fraction. So we get 35.167. Now, what they're asking us to solve for here, predict the year during which the population will hit this amount. So the year that this all started in was 1980. So if I add the 35.167, what year will this happen in? So even if you wanted to come back here, 1980, add on that decimal, it's going to be happening during 2015. The 0.167, you could even think of that as being, you know, early on in the year. If it was 2015.5, that would be about halfway through the year. 2015.9 would be towards the end of the year 2015. So during what year? It's going to be during 2015. Okay, now we can answer the same question, or at least get the same answer, with the power rule. Just going to show you both in this example, and then in the other questions we'll just choose one. So I'm just going back to where we isolated the base of 1.022. So if I was going to use the power rule, that means I'm going to take the log of both sides. And again, the reason I bring logs into the problem, I'm again just using a common log, is so that I can take that exponent and use the power rule of logarithms, which means I can bring it down in front. By doing that, I'm now able to isolate that variable, because I can divide away the log of 1.022. And we should also get that 35 value. Let's just confirm it. So I have the log. I'm going to go up and find that number. Here we go. So the log of that divided by the log of 1.022 gets us that same value, 35.167. And we would add that again to 1980 and get the year 2015. So again, I'm showing you both ways, not because I would ever need to see you complete this question in both ways. I just want you to be comfortable with either of them. So the power rule, take the log of both sides, bring down the exponent, or the conversion to log form, just use the loop trick. Both of them, though, need you to isolate the base in order to begin. Okay, what I'd like you to now do is take a moment to read through number 2. See if you can maybe set up what they're asking you to find, maybe set up the first step, pause the video, and then we'll start together. Okay, so we have this question. They tell us the temperature after an oven is turned on, its temperature T is represented by this equation. Okay, M is the number of minutes after the oven is turned on. T is the temperature of the oven. We already have that in degrees Fahrenheit. Okay. How many minutes does it take for the oven's temperature to reach 300 degrees Fahrenheit? And we're going to round to the nearest minute. So we're solving for M, which means we're solving for the exponent, and they gave us a T. So we should have T plugged in for as 300. And let's now try to solve for this exponent. So whether you're using the conversion or the power rule of logarithms, at this point you need to isolate the base, and the base is the 3.2. So I need to start undoing some operations here. It is very, very tempting to want to do something here and say that this is 50, right? But unfortunately, these are not like terms because the 350 or the negative 350 is being multiplied by the 3.2. So the raised to the power. So the only option I have to start undoing these operations is to subtract the 400. So if you fell into that trap and you have a 50 there because you subtracted, you are not alone. That is one of the more common mistakes to make here. The first step would need to be subtract the 400. And then I still have one more step before I've isolated my base of 3.2. Now I'll divide by the negative 350. Okay, so negative 100 divided by, negative 100 divided by negative 350. If you want to, again, you could use part of the decimal. It's a kind of a nice simplified fraction of 2/7, so maybe I'll use that. 2/7 is equal to 3.2 to the negative 0.1 m. So I'm just going to use the conversion on this one. So I'm going to use the converting to log form. So converting to log form. So we're going to circle the base, run the race. So we get a logarithm with a base of 3.2 of 2/7 is equal to negative 0.1 m. And then all I'll need to do after this is divide to get it completely alone by the negative 0.1. Okay, so m is equal to this whole thing calculated. So let's go to our calculator, alpha window choice, choice 5. Let's put the base. Sorry if you hear my son upstairs crying. He doesn't want to go to bed. Okay, so I have a log with a base of 3.2 of 2/7. And now I'm going to divide this by negative 0.1. And we get 10.77. Sorry, guys. 10.77. Let's just zoom out a bit. All right, to the nearest minute. So we should get 11 minutes. Okay, 11 minutes. Final answer to this one. Okay, then one more question. Number 3. So again, I'd like you to just pause the video, read through it, maybe see if you can set up the first step, and then we'll start going over it together. Or if you want to try the whole thing and then, pause the video, try the whole thing, unpause, we'll go over it. Okay, so for this question, it's giving us the number of bacteria present in a petri dish can be modeled by this function. So we have n is equal to 50 times e to the power of 3t. Again, e is that irrational constant, approximately 2.72. That's the base of this exponential function. They tell us n is the number of bacteria present after t hours. And we're being asked to find, to the nearest hundredth, the number of hours it will take for n to be 30,700. So we're solving for time. N is 30,700. So I'm going to plug that in for n. That's going to be equal to 50 times e to the 3t. So we want to get the base alone. The base is just the e. So we're going to have to divide the 50 So if you started converting into log form and you circled the base and the 50 was part of that base, it's tempting to do that, especially when, I don't know why it's more tempting for some students when you see E as the base. E is the base. Imagine there were parentheses here. It's the only thing being raised to the variable power. 50 has a power of 1. So 50 needs to get divided over to the other side. Otherwise, I cannot say that I've isolated the base and then I'm not ready to go into log form or, use the power rule. So maybe for this one, I'll do the power rule. So if I take, so I'm going to use the power rule of logs. That does not look like an R. Okay, so that would mean I'm taking the log of both sides. Okay, power rule allows me to take the power, bring it to the front. So now I have 3t multiplying the log of E, and I have the log of 614. Again, you could really just divide by the log if you want. So if we did that first, let's say I could divide by the 3 at the same time, but let's just do it step by step. So log of 614, again, I'm using the common log. You can use any log you'd like, but that's the easiest one to use if you're taking the log of both sides. And then I have the log of E, so second division. You also could have used ln since we are using base E, but it doesn't have to be done that way. All right, so we get 6.419. Again, I'm not rounding. And then I do need to divide by 3. I get 2.1399. And this asks us to round to the nearest hundredth of a year, so 2.14 years. Okay, so I would recommend if you're just struggling with the algebra to go back to lesson, what's this, lesson 7? Go back to lesson 6 and just review. Maybe if you didn't get a chance to work on the practice questions, maybe give a few of those a try, because lesson 6 is just really helping you with the power rule, which is what we just did in number 3, or using, the converting to log form using the loop trick to just solve. And then come back to this lesson. There are practice questions for lesson 7, like there always are. So these answers will be posted later on Canvas with the rest of the notes. Please, take a look at them. Maybe give a few of them a try before you look at the homework. And then homework 7, just submit on Canvas when you get a chance to complete it. Thank you.